where theory meets the shop floor. No shortcuts, just real engineering and technical expertise. Let's get into it. Welcome to this video on the CNC Machine Accuracy Budget, or CMAB. This quantitative framework is designed for condition-based precision maintenance. Traditional maintenance overlooks the fact that encoders measure axis position, not physical part geometry. This leads to reactive, time-based, or partial condition monitoring strategies that often result in defective parts before alarms are triggered. CMAB bridges the gap between machine design, physical testing, and operational maintenance. Unlike other methods, CMAB systematically combines mechanical tests, weighted sensitivity, and real failure data into a single actionable score. The CMAB architecture follows a four-level process: define, weight, score, and act. This transforms raw diagnostic data into specific maintenance actions. Level 1 involves defining a universal taxonomy of 17 geometric, dynamic, and electronic accuracy parameters. These are measured using tools like laser interferometer or ball bar and mapped to specific components. Matching diagnostic tools to machine kinematics is crucial to prevent collecting meaningless data. Tools like the laser interferometer are mandatory for certain measurements, while others, like the ball bar, may be mechanically meaningless for specific machines. Level 2 and 3 involve calculating the score. We use a quadratic penalty model, where the penalty is the square of the ratio of the measured value to the tolerance limit. This heavily penalizes parameters approaching tolerance and ensures alarms are triggered early. The composite score directly maps mathematical health to condition-based maintenance strategies. Scores range from excellent, requiring standard maintenance, to critical, requiring immediate intervention. Applying the framework to a specific machine, the PMC Threader Model 468 shows that encoder signal integrity is the primary root cause of catastrophic defects, receiving the highest weight in our calculation. The accuracy stress profile, visualized here, reveals localized degradation, indicating the spindle encoder subsystem is absorbing the most mechanical stress, even before tolerance breaches. For the pilot machine, the final CMAB score of 0.48 places it in the yellow zone. This mandates a shift to enhanced PM and predictive maintenance, including increased inspection frequency for key parameters. The Parameter Criticality Index, or PCI, directs technicians to the exact subsystem needing attention. In this case, encoder integrity, thread lead, and Z backlash are the top contributors to the score. Trend analysis calculates remaining accuracy life, or RAL. By projecting the score trajectory, we can precisely schedule interventions one production window before the machine produces defective parts. CMAB drives significant operational benefits, including increasing mean time between failures and reducing mean time to repair via surgical troubleshooting. It also improves product quality and enhances team development. The implementation roadmap details scaling the pilot into a fleet-wide standard. Future phases involve validation, calibration, and finally, digitizing the framework into real-time dashboards for continuous monitoring. Thanks so much for watching. I truly appreciate it. I'll catch you in the next one. Until then, keep building and stay curious.